Alright, in this video we're going to talk about logarithmic scales dealing with earthquake sounds and acids. This video is section 8D and this will wrap up chapter 8. Alright, in this unit we're going to explore three important scales that are related to logarithms: magnitudes, decibels, and pH. They are commonly called logarithmic scales, which makes sense if you remember that logarithms are powers. Now, in one of the videos that we talked about, I did give you a short review about what logarithms are. I believe that was section 8B. So you might want to review that video as well. Alright, let's first talk about the magnitude scale for earthquakes. Earthquakes are a fact of life for much of the world's population. In the United States, California, and Alaska are most prone to earthquakes, although earthquakes can strike almost anywhere. Scientists measure earthquakes' strength with the earthquake magnitude scale. The magnitude is related to energy released by the earthquake, but each magnitude represents about 32 times as much energy as the prior magnitude. For example, a magnitude of 8 earthquake releases 32 as much energy as a magnitude 7 earthquake. Well, it should say 32 times as much energy as a magnitude 7 earthquake. Okay? Now, let's talk about the earthquake magnitude scale. And that's this. The magnitude scale for earthquakes is defined so that each magnitude represents about 32 times as much energy as the prior magnitude. The magnitude, which is M, is related to the release energy, which is capital E, by the following equivalent formulas. And these are the two right here. Log to the base 10 of E is equal to 4.4 plus 1.5 multiplied by M. Or, this can be converted to this one. E equals to 2.5 times 10 to the 4th multiplied by 10 raised to the 1.5 M. Now, the latter formula, which is what E is equal to, that's the one we'll be using in our examples. The energy is going to be measured in what they call joules. Magnitudes have no units. Okay, now, I won't talk about what joules are, but if you're taking a physical science class, your instructor for that course might help you understand what that unit means for energy. Okay, now, example 1 is just asking the question about what is the magnitude scale for earthquakes. What increase in energy is represented by an increase of 1 magnitude on the earthquake scale? And you'll have to read through the answer choices and pick which one best answers that question. Okay? The magnitude scale for earthquakes, we already talked about that. It is the scale that scientists use to measure the strength of an earthquake, and an increase of 1 magnitude on the earthquake scale represents about 32 times as much energy as the prior magnitude. So it'll be that answer choice there. Okay. Alright, now let's look at this example. Now we're going to find out how much energy in joules is released by an earthquake with a magnitude of 6. And we have to give the answer in what they call scientific notation, using the multiplication symbol in the math palette in your My Math Lab homework as needed. and I do need to inform you, if you're not familiar with scientific notation, on Canvas, I do have review videos that will explain what scientific notation is. So you might want to watch those videos in order to get an understanding of what scientific notation is. Okay, because that's what we'll have to give our answers here. Now here we're going to use that formula. E is equal to 2.5 times 10 raised to the fourth, and that's multiplied by 10 to the 1.5 m. M represents the magnitude of that earthquake. And here, the magnitude here, that's your m, that's going to be 6. So we just substitute m in that formula here. So this will be E equals 2.5 times 10 to the fourth times 10 to the 1.5 times 6. Now if I multiply 1.5 times 6, I'm going to get 9. So I have E is equal to 2.5 times 10 to the fourth times 10 to the 9. That came from 1.5 times 6. I just multiplied those two. Okay, now what I'm going to do here is group powers of 10. So this one I'm going to have E is equal to 2.5. Now I'm going to group the 10 to the fourth and the 10 to the 9th in parentheses. So I got 10 to the fourth times 10 to the 9. There's a rule for powers of x when you're dealing with exponents. When you're multiplying powers of the same base, we're going to add the exponents here. So I'm going to bring the 2.5 times, bring over the 10 and add 4 plus 9, which will give us 13. So this will be the answer in scientific notation. 2.5 times 10 to the 13th power. Alright, let's take a look at example 3. And this is similar to example 2. I'm just going to change the 6 to a 4. Here we're going to find out how much energy in joules is released by an earthquake with a magnitude of 4, not 6. Okay, because that's similar to example 2. So I'm going to use that same formula. E is equal to 2.5 times 10 to the fourth times 10 to the 1.5 times m. 10 raised to the 1.5 times m. In this case, we just substitute m with, in this case, 4. So the E is equal to 2.5 times 10 to the fourth, and that's going to be multiplied by 10 raised to the 1.5 times 4. Now if I multiply 1.5 times 4, I'm going to get 6. So E is equal to 2.5 times 10 to the fourth multiplied by 10 to the 6. Okay. Again, I'll group 10 to the fourth and 10 to the 6 together. So I have 2.5 multiplied by 10 to the fourth times 10 to the 6. And again, when you multiply powers of the same base, you're going to add your exponent. So I'm going to have 2.5 times 10 to the 4 plus 6, which would be 10. So in scientific notation, the amount of energy in joules will be 2.5 multiplied by, 2.5 times 10 to the 10th power. Okay. Alright, let's look at one more of these. Use the earthquake magnitude scale to answer the following question. Compare the energy of a magnitude 8 earthquake to an explosive that released 18 times 10 to the 18th joules of energy. Okay? So here we need to find out what the energy of a magnitude 8 earthquake. So our M is going to be equal to 8. And our formula is that E is equal to 2.5 times 10 to the 4th times 10 raised to the 1.5 M. And M in this case will be 8. So your E is going to be equal to 2.5 times 10 to the 4th times 10 to the 1.5 times 8. And 1.5 times 8 will be 12. So I got E is equal to 2.5 times 10 to the 4th times 10 raised to the 12th power. And that came from 1.5 times 8, gave me 12. I'm going to bring down the 2.5, and I also know that if I multiply powers of the same base, I can add the exponents here. So this will be 10 to the 4 plus 12, which is 16. So here, the energy for a magnitude 8 earthquake will be 2.5 times 10 to the 16th power. Now we want to compare that to the energy, compare that to the explosive device that released 18 times 10 to the 18th joules of energy. So I'm going to take that 18 times 10 to the 18th, divide that by 2.5 times 10 to the 16th. Now here, this is what we do here. We take the first part, the 18, divide that by the 2.5, which I came up with is 7.2. Now, there's a rule that says when we divide powers of the same base, we subtract the exponents here. So when I divide 10 to the 18th by 10 to the 16th, bring over the 10, but we subtract 18 minus 16, which will give us 2. So it'll be 7.2 times 10 to the 2nd. But they want that as a whole number. And I know 10 to the 2nd is 100 if I write it out as a whole number. Multiply 7.2 times 100, you'll get 720. So here the explosive device, it releases about 720 times as much energy as a magnitude 8 earthquake. Okay. Alright, next we'll talk about measuring sounds in decibels. That's the next thing we'll look at. That's the next scale. The decibel scale is used to compare the loudness of sound. Now, the loudness of sounds in decibels is defined by the following equivalent formulas here. Here, we got the loudness in decibel, which is dB, and that's equal to 10 times log to the base 10 of this quantity, the intensity of the sound divided by the intensity of the softest audible sound. Or we can use this formula right here. The intensity of the sound divided by the intensity of the softest audible sound, that's equal to 10 to the loudness in decibels divided by 10. That right there is an exponent. I think more than likely we're going to be using this formula right here to find out the loudness in decibels here. Okay. So now, example 5 just is a basic question that we just got through talking about here. In this case here, what is the decibel scale? And describe how it is defined. Okay, so the first part, what is the decibel scale? Well, it's a scale that's used to compare the loudness of sounds. We just got through talking about that. So it'll be answer choice A. Okay. And how is the decibel scale defined? Well, here you'll be given a choice of answers in the drop-down menu for each one of those here. So here, it is defined so that A, either a sound, a substance, or an earthquake. Here we're dealing with sounds, since we're dealing with decibels, so we obviously will choose that. That a sound of 0 decibels, abbreviated 0 dB, represents, and in this case, on the next page I'm going to show you this. The softest audible sound, when you have 0 decibels, that would be it. 0 decibels, that would be the softest audible sound. So here, we're going to choose the softest sound audible to humans. Okay, because of no acidic and measurable earthquake, most basic substance, complete silence, no ground movement, those don't make sense. It's the softest audible sound for 0 decibels. Okay. Alright, now on the next page, we're going to use that table that I just showed you to answer this question, example 6. How many times as loud as the softest audible sound is the rustle of leaves? Well, the softest audible sound is 1 times as loud as the softest audible sound. So the rustle of leaves, if you look here, it is going to be 10 times as loud as the softest audible sound. So here we just answer that question by saying 10. 10 times as loud as the softest audible sound for the rustle of leaves. Okay. Now, the formula that I just showed you is the one that we're going to be using in example 7. What is the loudness in decibels of a sound 10,000 times as loud as the softest audible sound? Now in this case here, we're going to have to use that formula. I have to write it out. The loudness in decibels, which is going to be dB in short, that's equal to 10 times log to the base 10 of the intensity of the sound divided by the intensity of the softest audible sound. Okay, that's the formula that I showed you on the last page here. And it's the first one that we're going to use here. Alright, so now let's do some substitution here. We got 10 log to the base 10. The intensity of the sound that we're dealing with is that 100,000. And the intensity of the softest audible sound, well, the softest audible sound has the intensity of 1. Okay? And we can get that from the table that I just showed you here. Okay? Softest audible sound has an intensity of 1. That's the one in the center. Now, if I do 100,000 divided by 1, that's going to be 100,000. So I'm going to have 10 to the log to the base 10 of 100,000. Alright, now if you want to, you can use the calculator here. I'll show you how that's done. Here we're going to have 10 times. Now, the log key is next to number 7 on your calculator. You press the log key, L-O-G, and that base 10 is understood to be there in the calculator. And then 100,000, close parentheses, hit enter. You'll get the answer of 50. So the loudness of this sound in decibels is 50. Okay. That's how you'll do that particular problem using this formula here. Okay. Alright, now, the next thing we're going to talk about is sound comparison. Okay, now the formula that calculates the loudness ratio of one sound to another will be this. The intensity of the first sound divided by the intensity of the second sound, that's going to be equivalent to 10 raised to the loudness of sound 1 in decibels. That should be loudness of sound 1 in decibels minus the loudness of sound 2 in decibels. That difference is divided by 10. And all of that is in the exponent for the base of 10. So, in example 8, we want to find out how much louder or more intense is a 59 decibel sound than a 20 decibel sound. Okay, so we're going to be using this formula up here, and I'll rewrite that. Intensity of sound 1 divided by the intensity in sound 2, intensity of sound 2. That's going to be equivalent to 10 raised to the loudness of the first sound minus the loudness of the second that's divided by 10. And all of this is in the exponent. So now, we're going to start with 10 to the loudness in sound 1. That's going to be the 59 decibel sound. So it will be 59 minus the loudness in sound 2 was 20. And that's difference is divided by 10. Now if I do 59 minus 20, that's going to be 39. So I got 10 to the 39 divided by 10. Well, 39 divided by 10 would be 3.9. So it'll be 10 to the 3.9. And if I do 10 to the 3.9, in the calculator, and they want that to the nearest whole number. This will be 7,943. So the 59 decibel sound is 7,943 times as loud as a 20 decibel sound. Okay. Okay. Next we'll look at the inverse square law for sound. Inverse square law for sound. The intensity of sound decreases with the square of the distance from the source, meaning that the intensity is proportional to 1 over d squared. Therefore, sound follows an inverse square law with distance. Okay, so in example 9, we want to find out how many times greater is the intensity of sound from a concert speaker at a distance of 6 meters than an intensity at a distance of 12 meters. Alright, so now we're going to use that 1 over d squared for a distance of 6 meters. We're going to use 1 over d squared. Your d is going to be 6, so it'll be 1 over 6 squared. And 6 squared is 6 times 6, which will be 36. So we know the intensity of sound from 6 centimeters is 1 over 30. Well, 6 meters is 1 over 36. And now for d equal to 12. Again, we're using 1 over d squared, but this time we're going to square the 12. So 12 squared will be 144. That's from 12 times 12. So we got 1 over 44. And now we want to find out how many times greater is the intensity of sound from a concert speaker at a distance of 6 meters than an intensity at a distance of 12 meters. Well, it's going to be a ratio of the two. So here we're going to have, in this case, 1 over 36 divided by 1 over 144. Now this is a complex fraction. Now, when we divide fractions, we always multiply by the reciprocal of the second fraction. So this will be 1 over 36 times the reciprocal. We flip 1 over 144 over, it will be 144 over 1. And we'll do 1 times 144, that would be 144. 36 times 1 will be 36. 144 divided by 36 will be 4. So the intensity of sound is going to be 4 times as strong at 6 centimeters as it is at 12 meters. 4 times as strong at 6 meters as at 12 meters. Alright, next we'll talk about the pH scale for acidity. And this deals with acids. For acidity, we use the pH scale. If you check the labels for many household products, including cleaners, drain openers, and shampoo, you will see that they state a quantity called pH. Okay. Now the pH scale is used to classify substances as neutral, acidic, or basic. And the pH scale is defined by the equivalent formulas here. Here, pH is equal to the negative of the log to the base 10 of H plus, or the H plus is equal to 10 raised to the negative pH. Now, H plus is the hydrogen ion concentration in moles per liter. Okay. You'll pretty much learn more about that when you take a physical science class, if you have to, or a chemistry class. Pure water is neutral and has a pH of 7. Acids have a pH lower than 7. Bases have a pH higher than 7. Okay. Now the concentration of hydrogen ions is denoted as H plus in brackets and is usually measured in units of moles per liter. A mole is simply a special number of particles, where 1 mole is approximately 6 times 10 to the 23rd particles. The numerical value of a mole, which is about 6 times 10 to the 23rd, is known as Avogadro's number. Okay, so that's something that's taught in chemistry. I won't go into much detail about that. Okay, and these are typical pH values here in this table here, as you can see. The numbers that are less than 7 are acidic, like lemon juice or vinegar, stomach acid, drinking water. Pure water is neutral because it is at 7. The last 3 are what they call basic. Baking soda, household ammonia, drain opener. They're basic because they're above 7. So here's a kind of a review question here, what I discussed in this video here. What is pH? What pH values define an acid, a base, and a neutral substance? Okay. So you pretty much have to pick which one will fit that particular question, and in this case it's going to be this one, because we did talk about the acidity of a solution is measured by pH. A neutral substance has a pH of 7. Acids have a pH lower than 7, and bases have a pH higher than 7. Okay, so now, in this example, suppose the pH of a solution decreases by 3. How does the hydrogen atom concentration change? Okay. Now, here's how we're going to attack this particular problem. Here I'm going to let Z equal to the initial pH. So here we're going to let Z be the initial pH. And that's going to mean your H plus, that's your hydrogen ion, that's going to be 10 to the negative Z power. That's the Z right there. Now if it's decreasing by 3, then your Z minus 3 will be equal to the new pH. Okay? And that means the hydrogen ion, will be 10 to the negative, and in this case, in parentheses, Z minus 3. Okay. So how does the hydrogen ion concentration change, well, we have to take the ratio of this. The ratio of the new pH, or the new hydrogen ion concentration, that's 10 to the negative, in parentheses, Z minus 3, divided by 10 to the negative Z. Now when we divide powers of the same base, we're going to subtract our exponent. So this will be 10 to the... Now, if I distribute the negative, this will be negative Z plus 3 minus the negative Z. Simplify this, this will be 10 to the negative Z plus 3, and minus the negative will be a plus Z. Your Z's will zero out. You'll be left with 10 to the third. Okay. Now they want this answer in scientific notation, so since there's no number in front, this is understood as 1 times 10 to the third. Okay. That will be scientific notation here. So the new hydrogen ion concentration will be 1 times 10 to the third times the initial concentration. So the answer, the other question, does the change make the solution more acidic or more basic? Well, the pH solution is decreasing by 3, so that means it's going to be more acidic. Okay? Because the pH has gone down. It's going to be more acidic. Okay, let's look at this next example here. A pH of a solution of 2.9. Well, is 2.9. Here we have a pH of a solution being 2.9. What is its hydrogen ion concentration? That's the H plus here. That formula that I just got through talking about, H plus, that's going to be equal to 10 raised to the negative pH. I'll pull that back up here. That's this formula, H plus, that's 10 to the negative pH. That's what it's equal to. And that is the hydrogen ion concentration here. So your pH was 2.9. So we do 10 to the negative pH of 2.9. This can be typed in the calculator. 10 hat and then negative 2.9. Make sure you use the negative key at the very bottom of the calculator and not that minus sign. The negative key is in parentheses, which is right here. And then hit enter. This will be your decimal, and I'll go ahead and write this out as 0.00125. They want that answer in scientific notation. If you recall, scientific notation is going to be written in the form where the first part is a number that is at least 1 but less than 10, multiplied by a power of 10. I need to place a decimal point behind the very first number that is not a 0. That means this decimal point needs to be behind the 1. So I need to move it 1, 2, 3 places behind the 1. So this will be, I'm going to say 1.258 times 10 to the, and I moved it over 3 places to the right, so the power of 10 has to be negative. So it'll be 1.258 times 10 to the negative third. and they want this to the nearest tenth or to 1 decimal place. So this part to the nearest tenth will be approximately 1.3 times 10 to the negative third. So the hydrogen ion concentration will be approximately 1.3 times 10 to the negative third moles per liter. Okay, let's look at the next example. What is the pH of a solution with a hydrogen ion concentration of 0.0001 mole per liter? Is this solution an acid or a base? Okay. So if we want to find the pH, we got to use this formula, negative log to the base 10 of our hydrogen ion concentration, H+. And here the hydrogen ion concentration is 0.0001. We'll substitute that in this formula, so pH is equal to the negative log to the base 10 of 0.0001. And you know what I'm going to do? I'm going to go ahead and use my calculator. Be easier to do it that way. The negative, we press the negative key. Oops. Press the negative key. And then press the log key on the left-hand side. It's already going to be to the base 10, so it'll be 0.0001. We type that in. Hit enter. Hit enter. And it's going to be, in this case, 4. Okay. So the pH of a solution with a hydrogen atom ion concentration of 0.0001 mole per liter is going to be 4. Now, based on that pH, is it basic or is it an acid or a base? Well, that 4 is less than 7. And if a pH is less than 7, it is considered to be an acid. If it's over 7, it is a base. And of course, if it is 7, it's going to be neutral. Okay, and finally, how many times more acidic is a solution with a pH of 4.1 than solution B with a pH of 10.1? Solution A has a pH of 4.1. Solution B has a pH of 10.1, and we want to find out how many times more acidic is solution A than solution B. Okay. Okay, so here's solution A. Has a pH of 4.1. And in solution B, there's a pH of 10.1. That means the hydrogen ion concentration of solution A would be 10 to the negative pH, which is negative 4.1. Okay? So here, I'm using that formula, the hydrogen ion concentration, that's equal to 10 to the negative pH. And for solution B, its hydrogen ion concentration would be 10 to the negative 10.1. So if I compare solution A to solution B, solution A is 10 to the negative 4.1. That's going to be divided by 10 to the negative 10.1. That's a ratio of solution A to solution B. 10 to the negative 4.1 divided by 10 to the negative 10.1. Now when we divide powers of the same base, we subtract our exponents, so this will be 10 to the negative 4.1 minus negative 10.1. Now if you do if you do negative 4.1 minus a negative 10.1 on your calculator, you're going to get 6. So it'll be 10 to the 6. Now again, they want that in scientific notation, but here there's no number in front of that. It's understood to be a 1, so it'll be 1.0 times 10 to the 6. That will be the formal scientific notation here. Alright. So, to answer the question, solution A is 1.0 times 10 to the 6 times more acidic than solution B. Okay? And that will conclude this video that deals with the logarithmic scales when we're dealing with earthquakes, sounds, and acids.